In the study of emergent phenomena, the simplicity of components of a system can often belie the complexity of the behavior of the aggregate. For example, sugar doesn't pour like salt. Fascination with such phenomena has led Professor Karen Daniels to a wide variety of research programs.
Emergent phenomena appear everywhere in the world around us. One place we've had a lot of fun looking is in understanding how frost can cause convection patterns to form in the grass on golf courses. So one of the things that fascinates me about sand is the fact that if I take a bucket of it out to the beach, I can pour it out into a pile, and while it's flowing it looks like a liquid. Yet as soon as it hits the ground, it's solid enough that I can walk on top of it. And this is a property that emerges from the interaction between the grains of sand. What can I do to a material that's composed of other materials? So sand is one example, but emulsions like mayonnaise or foams like shaving cream all have this property, that they're a material that's composed of little bits of other things that are assembled into a larger whole. What is it about that larger whole that behaves collectively when the individual particles don't? If you want to build a bridge and have the embankment remain intact, you need it to behave like a solid. And our ability to control whether or not the material behaves like a fluid or behaves like a solid is at the heart of many engineering applications. So one of the things we've learned in our laboratory experiments is that if you squish a granular material, not all of the grains of sand share the pressure equally. There'll be some grains of sand that form a line of force chains, and they're supporting a large fraction of the weight of the system. If that chain of grains were to buckle, the whole system could collapse. A lot of analytical techniques in the field and a lot of computer simulations in the field make use of circular or spherical particles. This is clearly not representative of the wealth of grains of sand and coal and cereals and pharmaceuticals that exist out in the real-world applications. So we've started using laser cutters to cut particles of more interesting shapes, things that are ellipses or star-shaped or pentagons, and examine how choices of different shapes influence the results of studies that we see. This is an opportunity for us to get out in front of what people are doing on simulations and discover new phenomena that have not yet been explained. Another kind of soft material are materials like gels, where they look solid. If you imagine Jell-O, if you cut your spoon into it, it actually makes a crack, and it can hold its shape for a while. So they are solid, but they're right at the boundary of behaving like a liquid. The question in understanding the material properties is, when should you model them as a solid that has some liquid properties, or when should you model them as a liquid that has some solid properties? And a place where this is becoming extremely apparent in recent years is the fact that a solid, in fact, has surface tension. We usually associate surface tensions with liquids, so this is what holds a raindrop into a circular shape. So if you imagine placing a drop of water on a sheet of glass, the surface tension of a liquid is so small compared to the strength of the glass that the glass stays perfectly flat. So if you consider soft materials such as, say, agar or gelatin gels, a droplet of water placed on top of one of them will actually pull up on the gel and make cusps in the surface of the very soft solid. So even though surface tension forces are very small, because the gel is so weak, liquids are able to deform the surface of a solid. So we're very interested in understanding in what kinds of gels these effects play a role. So is it just a mechanical effect, that if the gel is hard or soft, that will affect whether or not the liquids are able to pull up and deform the surface, or are there chemical effects as well? So earthquakes are a tremendous hazard in many parts of the world, and they have a number of features that make them difficult to engineer around. One is that it's unpredictable when they will happen. Another is that once they do happen, they create ground motion that fluidizes granular materials and it starts to move. And a problem in us understanding how to mitigate those hazards is that we can't conduct experiments on the Earth. An advantage of laboratory experiments is that we can run them in what theorists would call periodic boundary conditions, namely design circular experiments where the particles go out one side and come back in the other, and therefore can run continuously. This allows us to build up catalogs of tens of thousands of events that represents millions of years of geologic record, not just human history. So one of the things that we've noticed is that as you shear a granular material, there are small particle slips all the time. And those small slips may or may not lead to bigger slips. By listening to the experiment through these piezoelectric sensors that we have at the outer wall, we can start to correlate the acoustic emissions from these small slips with whether or not a larger event then later happens.
From systems as soft as shaving cream to ones as violent as earthquakes, viewing complex systems in light of emergent phenomena provides the focus of research of NC State faculty members like Professor Karen Daniels.